Hello everybody, I am Federico Uriati, PhD student from the University of Parma. In this presentation I will show you the result of our work developed in collaboration with my supervisor Professor Gianni Nicoletto and the industry partner BIMIT. The title of the research is Design, Production and Fatigue Testing of an Optimized Structural Component made of laser powder bed fused aluminum alloy. In the context of this work, we will focus on metal additive manufacturing and in particular laser powder bed fusion. The key advantages of these technologies are the possibility to realize complex parts characterized by features that are not possible to be produced with subtractive methods, and the short lead time compared to conventional processes. From the research perspective, few examples are available in literature about the development of additive manufactured part for structural use. In this sense, the aim of our work is to propose a full workflow and a real example for the development of a structural part from the identification to the physical testing. In this work, the additive manufacturing part development is divided in three main steps. The first is design, that is the definition of an integrated design workflow for the metal additive manufacturing realization. The second is the production, that requires a proper knowledge about equipment, material, job preparation, and process parameters. And the last, the qualification of the part, which means the fatigue testing of the real component under realistic working condition. For the definition of the workflow for the integrated additive manufacturing part design, the first step is the part selection, identifying the part of interest to be reduced with additive manufacturing. Then, the design space is defined, defining the dimensional restriction, the material selection, and the geometrical specification. After all, the topology optimization can be performed with definition of objective, boundary condition, and loads. After that, an iterative process needs to be respected. An iteration indicates the procedure that the designer has to follow to reach the optimal result. The result of the topology optimization needs to be selected and validated with finite element analysis from the designer until the stress distribution reaches the expected condition. After the definition of the first geometry, it is possible to start with the job preparation in terms of best orientation of the part in the build chamber and support generation. If some problem occurs in this phase, it is necessary to go back to the modeling phase. Finally, if the job is successfully generated, it is possible to run the process simulation to avoid excessive deformation and eventual problem. If this last step has a positive outcome, it is possible to go and continue with the production of the part. The case study of this work is a real low sport car lower suspension arm, selected for its interesting working condition. The part was scaled to be easy to produce and tested, and they featured changing the joints to simplify the load application during simulation and testing. After the part selection, both design and non-design space are defined, and the material selected in relation with the load that the component has to sustain. Then the topology optimization is performed using a software. The first thing to do during the optimization is the definition of the objective, and the first goal was the minimization of the mass, respecting a safety factor of 1.6. After that, a maximization of the global stiffness. The result of the optimization were many, but we selected the solution that gave the best stiffness to weight ratio. That is the one here reported. The result of the topology optimization is a raw mesh that can be seen as a suggestion for the designer for further remodeling. Remodeling and finite element validation are two iterative processes that can be executed one followed by the other to obtain the optimal result. The iteration is concluded when the stress distribution is under the stress limit that is defined by the designer. Job preparation and process simulation are also the two steps that require an iterative procedure. Definition of the best orientation of the part in the build chamber and an optimal support generation are very important to obtain the best results during the manufacturing. As well, process simulation for evaluation of deformation and main residual stress is very important to avoid problems during the preparation of the part. If any problem occurs during this step, it is necessary to go back to the previous step to make change and apply correction. At the end of the design phase, it's possible to start with the production of the real part. In collaboration with our industrial partner, BIMIT, we had the opportunity to have access to the most advanced fabrication equipment. In particular, in this work, we prepared a job using an SLM 500 machine using aluminum silicon 10 magnesium alloy. Here are reported the main process parameters as laser powder, scanning speed, layer thickness, etch space, and the information about the post-process which underwent the part produced during the same job. The job is the one reported on the picture on the left. 10 parts were produced with two different orientations, A and B, with the aim to observe and investigate the different effect of the orientation and the support position on the fatigue properties of the part. In parallel, 64 directional fatigue miniature specimens were produced to evaluate the fatigue properties of the material using the method proposed by Professor Nicoletto in 2017. The four different orientations, A, B, C, and 45 plus, allow us to observe the anisotropic fatigue behavior introduced by the process on the material. Finally, two Amphion calibration specimens were generated with the aim to calibrate the process using the Amphion calibration process, Amphion simulation process that works on the inherent strain method. After the design and the production of the actual part, it is important to qualify the real fatigue strength of the additive manufacturing part. In the laboratory of our research group, we were able to build a testing setup to reproduce the real loading condition that the part has to sustain. A dynamic load was applied and fatigue testing performed. In parallel, an elastic stress finite element analysis was performed to observe the stress distribution. In this first step, the failure on the first component occurs after 156,000 cycles in the exact position that was coincident with the maximum stress obtained with the finite element analysis. The qualification step includes also the possibility to use the result of the process simulation. Many information were obtained from the investigation, and it is necessary to put all the aspects together to have a comprehensive overview of the performance and being able to forecast future results. The residual stress distribution obtained with the process simulation software allows to see how are the value of the residual stresses in the point where the failure occurs, and as well evaluate the residual stresses on the flat surface of the miniature specimen. In this case, here are reported the results of the residual stresses evaluated on the flat surface of vertical and horizontal miniature specimen. It's possible to see in the plot in the middle that residual stresses on the type C specimen, that is the horizontal one, are much higher than the one on the horizontal orientation. These results can be linked with the results of the fatigue testing performed on the same material. Type A- orientation, which is also characterized by a lower residual stress, exhibits a higher fatigue limit. In contrast, vertical specimen type C show a lower fatigue strength, probably related with the much higher residual stress which influence the fatigue behavior. Results of finite element analysis, process simulation, and experimental fatigue strength will be used in the future development of this work to understand the performance of additive manufactured part and develop a forecast model. In conclusion to this work, we were able to recognize that the design of a component to be produced by laser-powered bed fusion is an iterative process which involves many steps prior to actual part production. Thanks to the collaboration with our industrial partner BMIT, we were able to realize a composite job incorporating actual parts, fatigue test specimen, and calibration specimen, useful for the collection of many data and for extensive testing. The anisotropic fatigue behavior of AlSi10 magnesium alloy obtained with directional specimen was attributed to the key role of fabrication residual stresses, and the prediction of the fatigue response of the optimized part benefited from the extensive modeling and simulation activities and ad hoc material testing.